We'll get started today and do a little bit more 12.2. I'm going to show you one equation and how to use it, and I'll give you some homework and go from there. So this equation right here, we'll go through what each of these symbols mean in a second, but it's delta U equals Q minus W. Well, delta U stands for the change in energy. Sometimes you're going to see it written as thermal energy. I think your book says that. Or internal energy. So they really mean the same thing, whether it's thermal or internal energy, they refer to the same thing. So you can change thermal energy in two ways, either making the temperature change. So higher temperature means more thermal energy, or the mass. So if either the temperature changes or the mass changes, you have more thermal energy if they increase. If neither of those change, you have no change in thermal energy. Q stands for the heat added to an object. And then W is the work done by the object. It's important to make the distinction that it's the work done by the object, not work done on the object. So for example, if you were to push a box, you're doing work on the box by pushing it. Let's say you're giving it 500 joules of energy. So that's work done on the box. What that means is that you are losing that energy right there. And you're giving it to the box. So you would lose 500 joules of energy, the box would gain that energy. So if you do work on the box, that energy is given to it. So work done on means an increase in energy to the box in this case. But if the box does work, it would lose that energy. So in this case, you do work on the box, you lose that energy. You do work on the box gains the energy. So what you could say based on that is that the work that you do on the box is equal to the negative of the work that the box receives. You could think of it this way too, that the work you do on the box would equal the negative of the work the box does on you. So while you give the box energy, you lose the energy. What you could say is that the box did work on you and took away your energy. So the work done on the box is 500 joules, that's positive. but the box did negative 500 joules of work on you by taking away your energy. Does that make sense before we go on? Just make sure that that is clear.
So it's just the reverse, correct?
Yeah, so if you're told that you do work on something, that thing can do work on you, but it's just the negative of whatever you did on it. Okay, let's look at an example using the equation I just showed you, delta U equals Q minus W. We'll look at a balloon expanding. With no temperature change. And we'll say no heat is added. Actually, I'm sorry. Let's take out the temperature change. Let's ignore that for right now. Make this less confusing for a second. Let's just say this instead. Just ignore that middle one and just say that the balloon's expanding and no heat is added. But there could be a temperature change in this example. So if the balloon's expanding, there's movement, there is work being done. Work is done by the balloon because the balloon is moving. And so if there's movement, there is work. But we said there's no heat added, so Q would be 0 in this instance. So use this equation right here. Delta U would equal 0 minus W. Delta U would equal negative W. And what this tells you is that there must be a decrease in U. Well, if delta U is decreasing, there's two things that could be happening. Either you're losing matter or you're losing temperature. So either temperature could decrease or matter could decrease. If the balloon's expanding, there's no decrease in matter. So there must be a decrease in temperature. So if the balloon expands and does work with no heat added to it, the balloon would decrease in temperature in this case. So this is how it'd be possible for there be to decrease in temperature with no heat being added to the object. So if something does work in the surroundings, it can lose energy, it can lose heat, it can become cooler. You can impart energy to objects in different ways. If you clap your hands, you have noticed, I've taught this before too, that by clapping your hands, you heat them up. And that's because you're doing work on your hands. You're imparting energy to your hands. You're increasing the speed of the atoms in your hands, and that makes the temperature rise in your hands. So if you slap a surface, you give it about an average of 24 joules of energy for every slap. The energy can go into heating up that surface. So let's say you're slapping a glass countertop. And let's say that you have 0.4 kilograms of glass that you're hitting. And every slap, you're imparting energy to the glass, which heats it up. And the question is, how many times do you need to slap the glass to heat up 1 degree Celsius? So how many hits to heat up the glass 1 degree Celsius? And we're assuming that it's not going to have any heat transfer to your hands, because your hands definitely do have heat. Your body is warmer than the glass. And so you would transfer heat based on your body warmth, but we're ignoring that for this situation. And we're assuming your hands don't impart any heat to the glass. It's just the work you're doing on the glass that heats it up. And we can use that to determine how many hits you would need to take to warm the glass up based only on hitting it and no heat being transferred from your hands to the surface. So we're assuming no heat transfer. And what that means is we're assuming that your hands are the same temperature as the glass. Okay, so in that case, we're going to use the equation delta U equals Q minus W. It said there's no heat transfer, so that means Q is 0 because there's no heat being transferred. So now the equation becomes delta U equals negative W. And it was said before that now we're doing work on the glass. When we slap the glass, we're doing work on it. So the work that we do on the glass would equal the negative that the glass does on the hand. So the work done on the glass is equal to the negative of the work that the glass does on the hand. And remember what W represents in this equation. It's what the object does to the surroundings. So we would put this into here. And we now would have delta U equals negative W, the work that the glass does on the hand. So now our equation becomes delta U equals the work that the glass does on hand. So we said before that there's about 24.2 joules of energy or work being done per slap. And what we're asked is how many times would we need to slap it to raise it 1 degree Celsius? So how do we find that out? At this point, our equation is delta U equals W. We know that W is 24.2 times X, but we don't know what U is at this point. Do you have this down so I can erase it? I'm gonna clear that. Okay, so delta U can be written with using MCAT. So if we're trying to find out the thermal energy, that's what U represents, we can use the MCAT equation to find out delta U. And once we know that, we can go from there. So we were given the mass of the glass. We can find C from our book in the table of glass. And then delta T is the temperature change. So the mass of the glass we were told was 0.4 kilograms. C of glass, look it up on page 318, 840. Delta T, 1 degree Celsius. We're asked how many times we have to slap to get 1 degree Celsius temperature change. So we're told it's 1 degree Celsius for delta T. Put those all in and let's solve for delta U. Okay, so that's our equation. Kilograms will cancel out, Celsius will cancel out. So we do 0.4 times 840 times 1. And that gives us 336 joules for delta U. So that means that we need to have delta U changed by 336 joules to get it to move 1 degree Celsius warmer. Remember the equation that we had? We had delta U equals work that the glass does on the hand. So now we have this. The work done is 336 joules. So that's the energy we have to transfer to the glass to heat up 1 degree Celsius. Now we're told that one slab gives you 24.2 joules. So if every slab gives you 24.2 joules, and you need 336 joules, we divide those two to get how many slabs you would need to raise it 1 degree Celsius. $336 joules divided by 24.2 joules per slab. That gives you 13.8. And of course, you can't have 1/8 of a slab or 0.8 of a slab. So our answer would be 14 slabs. We round that up to 14. You with me on that?
Yes.
Okay.
Yes, ma'am.
I'll go ahead and try another example. These can be tricky, but let me know if you're stuck or not, you're lost in the step. Okay, for this one, let's say you're heating up a cup of water over a flame. To boiling. If the flame gives you 270 joules per second of energy, how long would it take to heat up the cup of water to boiling if it starts at room temperature? So the cup of water originally is at room temperature. That's 20 degrees Celsius. We want to get it to boiling, which would be 100 degrees Celsius. And the question is, how long would it take to reach boiling point? So we're going to use the same equation we did before. Delta U equals Q minus W. Now what happens in this case? We're not doing work on the cup of water. We're not moving it. We're not stirring it. So no work is being done. So work is 0. We are giving it heat though. So in this equation, we have delta U equals Q. And we also know that delta U can equal MCAT, like I showed you in the last equation. So we would use this equation again to find the heat imparted to the cup of water. So what we want to do is find out how much energy would be needed to move it from 20 degrees Celsius to 100 degrees Celsius. We'll start with that and then go from there. Oh, sorry, I was on mute. We'll plug in the values we've been given and solve for delta U. So we know the mass of the water. So 1 cup of water, you don't need to know this, but 1 cup of water has a mass of about 0.23 kilograms. So that's just given to us in the problem. We don't need to know that. So that goes in for mass of the water. C of water, look up on the periodic table, or not periodic table, look up on page 318 and find it. And we would have the mass of the water times 4,180 joules over kilograms times degrees Celsius. Times temperature change, we would do T final 100 minus 20. multiply it out and go from there. So when you multiply out these numbers, you get for delta U 80,256. The question would be, how long would it take to heat up the cup of water over a candle flame if the candle flame gives it 270 joules per second of energy? So we know that the flame gives it 270 joules per second. We need to give it 80,256 joules. How long would it take to do that? So just divide these two. Take the total energy we need to impart to the cup of water and divide it by the energy of the flame per second, 80,256 joules, divided by 270 joules per second, gives us 297 seconds, which is about 5 minutes. All right, any questions about that?
No, that makes sense.
Okay. So today for homework, you look in your books on page 328. Do 22 through 26.